Hey, this is Dr. B, and let's talk about chromatography and distillation, two of the most common methods to purify mixtures. I've shown some images here to cut right to the chase. What you see here is a couple different chromatography methods and a couple of different distillation methods. Maybe you've seen some of these before. Maybe you've done some of these before. What we'll talk about is the various types, what they're typically used for. In other words, what's the situation? What's the right tool for the job? The parts involved, so you can talk the lingo, and it also gives you an idea of the basis for the separation, which is the final topic. After this, I'll have one slide where we'll just sort of quiz you to see if you got it. Okay, so in terms of the type, this is called paper chromatography right here. There it is. And all you do is spot a little bit of, oh, I don't know, some magic marker ink, for example, on here at the bottom. We'll call that the baseline. We stick a solvent in it. If it's a water-based ink, we might just put water in there, let it elute, E-L-U-T-E, up that piece of paper. And the substances that stick to the paper have low retention factors. They tend to stay low. Retention factor or RF value will vary from 0, meaning baseline, to 1, meaning the solvent front. And you can kind of see the solvent front right along there. So about 1 for that and 0 down there. Looks like this brownish stuff has a relatively lower retention factor, but not by much, right? You can also do it three-dimensionally rather than just use a sheet. We run it down a column. We call that column chromatography. Same thing. You've got some kind of stationary phase. This could just be purified sand. You run your mixture through it, and if it sticks to that sand, it has a low RF value and doesn't tend to run through the column. But if it's greasier, like the blue stuff, it'll slide right down, and you get it out first. And it looks like we're getting an excellent separation here of the brown stuff from the blue stuff. Distillation looks like this. So you're going to separate liquids based on their boiling points. Heat it up. The lowest boiling components will boil. They'll turn into gases. They'll run up through a column. They'll go down into a condenser to make sure they turn back into a liquid. And then you collect each fraction in a receiving flask. Lousy separation here, because look at how short this thing is. If you want good separation, have a nice big column in here. The more surface area, the better the separation. So if you had, for example, dissolved solid mixtures, that's suitable candidates for chromatography, right? If they're small amounts, you better use just paper or what they call thin layer of something on your stationary phase. It could be just silica gel or other things. If you add a lot of stuff, you better go with a column, and columns can be up to several feet wide to scale up. For distillation, you need a liquid-liquid homogeneous mixture, like, for example, ethanol and water, oil, motor oil, solvents, or water that you want to purify. And you just heat them up, separate them. Low boilers come over first, high boilers come over second. Let's make sure we can identify some of the parts. See if you can identify 1 and 2 here, and 1 through, let's say, 7 here. Since number 1 is the stuff that is not moving, we call that the stationary phase. The solvent that you choose is called the mobile phase. And by the way, if you use a polar solvent, like say something watery, like water itself or methanol, something like that can hydrogen bond, it'll tend to overcome the intermolecular forces of what things are sticking to the paper there and increases the RF value of everything. If you lower it and use a greasier solvent, like say hexanes or hydrocarbon or something like that, well, it doesn't have strong intermolecular forces. It will not overcome them as much, and the RF values of everything will be lower. For these, let's identify parts 1 through 7. Let's call 1 the pot. 2 is our column, which there really isn't one here, so this is a simple distillation. But here we've got a column, so it will fractionate. So it's a fractional column. And number 3 is right there. You bet, it's a thermometer, and it should be stuck in there. Otherwise, all your gases would just leave right there. Because at this point, they're gases, right? It's not till they hit this part here, which we call the condenser, that they condense. Number 4 is a receiver. So it can be as simple as a flask like you see there. Number 5 is super important. It's an open hole because these are gases and they will pressurize your system. So do not attach something so it's an airtight system. Always have a vent. And if you wanted to, in this case, you can go ahead and apply a vacuum to it, right? Put a vacuum device on here and you will get everything to boil at a lower temperature, which decreases decomposition. Good idea for this external jacket here to put the water in number 6 so it will, as it fills up, the water will go into that external jacket, making everything nice and cold, fill up this thing here, and comes out at position 7. Good. The basis for separation, as we said, was how sticky it is to your stationary phase, right? Here's an actual chromatogram of a ground up leaf dissolved in acetone. And we ran this up in mostly hexane, so pretty greasy substance with a little bit of acetone to try to give a nice variation of some of these things have RF values of 0.1, like chlorophyll A, or carotenes, which have a RF value of just about 1. And so you could easily separate out this stuff, probably the xanthophylls, and here, not bad. We're getting some pretty good separation. For distillation, the basis for separation is much simpler. Low boilers come off first because they have weaker intermolecular forces or fewer of them, and the higher boilers come off second, and you get better results with increased surface area as long as the stuff doesn't decompose, which will show up in this list of questions here. So give these questions a try. Can you list the numbered parts? Pause if you need to. Number 1 is the stationary phase. So I guess 2 you'd get. That's the mobile phase. Here we've got a pot, and I'm going 1 through 7. We've got a column, although it's missing. We've got a thermometer, so I should point out, and this is new information, that this means that this is not only a separation method, but it's also an identification method, because if that's reading 78 as it distills over, that might be ethanol. 100 might be water, and I'm talking Celsius. 5, make sure it's an open system or apply a vacuum. 6, water in, 7, water out. Now you got some Texas light crude light, sweet crude oil. How are you going to separate it? Distill it. It's a large amount of a liquid homogeneous mixture. You only got 1 drop of ink, which is a solution of a solid in a solvent. I'd go with a two-dimensional chromatography system since it's so little, either paper or much better thin layer chromatography like this one, much higher resolution than paper. You've got a liter, but I really should say a kilogram since it's a solid of ink. Well, you can't distill it, it's a solid, so you better go with chromatography, but you will severely overwhelm a TLC sheet, right? Thin layer chromatography sheet. Better go with column chromatography. Ethanol and water, that's a liquid homogeneous water, nice candidate for distillation. And simple might be enough because they have a difference in boiling points of 22 degrees. And if you were going to distill things, what is that basis for separation? You might recall it's just the intermolecular forces, which gives you really differences in boiling point. And more surface area gives you better separation. RF stands for retention factor. Gives value of 0 means it didn't move, 1 means it moved all the way. How do you increase that retention factor? Well, there's a couple ways. Most common ways is to increase the polarity of your mobile phase. Switch from hexanes to acetone, or maybe even water, and it'll push everything up. You can, and it's not done as often, change the polarity of your stationary phase. Sometimes they have these plastic sheets. They are greasier. They will make it so the RF values of everything tends to increase. So increase the polarity of the mobile phase or decrease the polarity of the stationary phase. And you want better separation. How can you do it for either method? Well, you can go a longer distance, right? You saw a giant column in the distillation slide on the previous slide, and you can use finer particles like here. The silica gel works better than paper, and you can use a better mobile phase here. Just choose one that gives you a better separation. If all your RF values are too high, cut it down. Too low, bring it up in terms of the polarity. Potential issues are myriad. For chromatography, sometimes you have trouble dissolving the stuff. Sometimes it's unstable. But let's face it, it's room temperature here, so your substances are unlikely to decompose. Polarity issues. If the polarities like this spot and this spot are super close, it might be hard to separate them. Distillation, the problems can be a little more severe. And by the way, chromatography tends to be very expensive. For distillation, the problems that you can run into is what if the thing just turns black when you heat it? That happens a lot. You might have noticed we said in the last slide that you can go with vacuum distillation, but maybe you don't have access to that kind of gear. So volatility can be an issue. If they have similar boiling points, you're going to run into a problem. And costs can be significant, but any moonshiner can tell you that this gear is relatively inexpensive and can be really scaled up easily. You know, just use a bigger pot and a bigger receiving flask, and you might be good to go for gallons, right? Okay, that is a summary of chromatography and distillation.